we're thankful that they did a renovation of Brown Hall, and there's not all that nice open glass in the front now, so it's a little bit better. Okay, if you're just getting in, you can take your time and log in and start MATLAB. We probably won't hit MATLAB until the end, toward the end of today. I want to first cover a little bit about the background of the material. What we're going to talk about today is how do we find a discrete time approximation of a continuous time model. Okay, so our continuous time models are like our differential equations. We convert them to S-domain. We use the Laplace transform. We get these transfer functions. In discrete time, we don't have differential equations. We have difference equations, and we use the Z transform, which I introduced last time we met. So let me give a little bit of motivation of why we're interested in doing this, and then we'll start going through how we do it. Question?
It's extremely hard to hear you back here.
It's hard to hear me?
Yeah. With the AC?
With the AC?
Yeah.
I don't control the AC, I guess. I'm out of control about that. And I don't know that there is a microphone up here. Now there is a white thing on the wall back there. Does that have an on-off switch? Try it. So I guess what we want to do is turn it up, I guess. Maybe the thing it. Oh, okay. I'll try to speak up a little bit.
Thank you.
Okay, so let me first draw the problem that we study in this class. We're assuming everything is in continuous time, so we're using S-domain functions. So everything we're studying in class is assuming that we're working in the analog world, the real world. So this is a typical control system. Okay, so I'm going to draw the model of the things that we analyze, the things that we will work on our project. This is what we analyze on paper, in lab. In our head, okay, so it'll be something like this. Look at the notation, okay, so just focus on the notation. I'm going to just draw a control system. I got a compensator that I'm going to call some dynamic system that I'm going to model as C of S. And then we've got a plant. This would be the simplest model that I could construct. Okay, this is the controller. This is the plant. This is the output. And this is the desired behavior or the reference. Hey, the control system works. The fan went down. Okay, now I can go back to my mumbling. All right, so the assumption is that every signal here, every arrow here, is a continuous time signal. So if somebody was to say, sketch the signal, you would say, okay, it might look something like this. Okay, you draw it continually, and the reference, is a signal that you say exists continually in time. All these signals exist continually in time, but this is real life. Okay, real life. What we have is the thing that we're trying to control. It certainly exists. We're not going to change that. But what happens is we put a sampler, which we model in our mind as a switch. It basically closes periodically, okay, and we get the information. Okay. As an example, my first job, real job that paid significant amount of money, I was living in Milwaukee, Wisconsin, but my parents, to this day, they lived in Knoxville, Tennessee, where I grew up. So whenever work breaks came along, Thanksgiving and stuff like that, like the good son, I would go home and see mom. That's about a 900-mile drive, okay? And you start at 4:30 in the afternoon after work and start that long drive through Wisconsin, Illinois, Indiana. About hour 5, you're around Indianapolis and you're starting to get a little tired. Now, what does driver's ed tell you you're supposed to do when you're tired and you're driving?
Keep driving.
What does driver's ed tell you you're supposed to do when you're tired? You're supposed to pull over and take a break. But of course, we're men, and men say,
Yeah, keep driving.
keep driving. That's right. And we're young men, and because we're young men, we think we are invincible, right? We are invincible, so we would just continue driving. And so this is the game that I would play. I observed that the highway has these rough sides, the rumble strips on the side of the road. And so I said, I am so tired. I'm going to not drive continually. I'm going to close my eyes. And I'm just going to kind of let the car kind of drift over to the side until I feel the wheels hit that rumble strip, and then I'll open my eyes up and then readjust and go on down. This will allow you to, rest your eyes for a second, 2 seconds, and I play these games to see how far I could go. So, but God is gracious, I'm still alive today. That's a very stupid thing to do. I should not have done it. But this is what I mean by sampling. Obviously, not looking at the road continually is not as good as, not looking at the road continually is not as good as looking continually, keeping your eye constantly on the road. So sampling inherently means you're going to lose a little bit of information. And on the front end, what we do is we periodically make adjustments. So obviously, if I'm driving my car and I'm not walking to the road, I'm just holding everything constant. I'm holding the wheel steady. And then I look at the road, open my eyes for a split second, sample what's going on, and I make an adjustment. I tweak the wheel a little bit, and I hold it constant till the next sample. Okay? And so this is what we call an analog to digital conversion. I'm periodically changing things. And so there's an A to D converter here. And mathematically, we model that as what we call a ZOH, or zero order hold. Zero order hold. We're holding the data for a while, for a period, and we describe that constant as a zero order polynomial. A zero order polynomial is a constant. That's why we call it a zero order hold. It's a constant. Things are constant for a period of time. This is a mathematical model of a to D converter. Okay. And then what we do is we take the sampled information and feed it back. So now what we have here is y of k. We have samples. We have samples of what's going on. We don't have this continuous signal, we have this sample. And then we bring it back here. And we have r of k here, which are samples of what we want to do. A list of commands in my computer. For the first hour, drive at 55 miles an hour from Milwaukee to Chicago because the traffic's bad. Then from Chicago to Gary, Indiana, you'll probably do about 45 miles an hour because the traffic's really bad. Then you get past Gary, Indiana, and then the next command is to drive at 75. Okay, so you just get a list of commands, that periodically change. All right. We would model y of k now as y of z. We would model r of k as r of z. So the notations change. Okay, notice that here's S of the domain is continuous time, Z is for discrete time. And of course, now all this information that I'm drawing here, this feedback and this information, it's all in a digital computer now. And now I have a computer algorithm which periodically does its job. Some of you are in the 3040 lab. You've been writing these little programs to check a button, and when the button gets mashed, you need to do something with your counter, make it reverse direction or something like that. And you're writing these for loops and while loops, which means that you do it periodically. You've written a routine to do a delay, do something and then do it again, and then do it again. So we model that as a computer algorithm, a C of Z. Okay. Some people will call this a digital filter. Okay. If you're a digital signal processor, you're changing the information, you're changing the signal, producing a new signal. You can call that a filter. But it's a digital filter. Okay. This is a program. A code. These are all the same words. Program, a code, a C program, a code. It does its work periodically. Okay. And so this is, again, samples coming in, and what's coming out is a sequence of numbers. Okay, just like in your 304 lab, you got a number being put out to 4 bits, it's a count right now. It's a counter. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, roll over. Okay, it's a count. And then this A to D converter converts it to an approximately continuous signal here. So what happens is it takes a number, holds it for a period of time. Takes a new number, holds it for a period of time. Takes a new number, holds it for a period of time. And you kind of get this stair-step function, which kind of approximates a continuous time signal. All right. So this is what we analyze. We're going to spend the majority of our time with this type of model, but this is what has to be implemented. So we're going to try to do 2 things today. We're going to first try to say, how do I approximate this? We're going to design this in class all semester. We're going to come up with these expressions that we're going to call the compensator, but they're in the S notation. It's assuming that we're going to, when we implement it, use op amps, transistors, those type of things. Okay, we seldom do that anymore. Okay, we seldom do that anymore. It's becoming a little bit of an art form. The number of people who know how to take a transfer function and turn it into a electronic circuit is getting smaller and smaller and smaller because of the advent of the digital computer. Now what we do is we have to get a program code. The problem is we design here, but we need this. So one of the questions is, approximation 1 is, I want to take, given this, how do we go to this, C of Z? Okay, Z is a discrete time model. All right. The second question that we have, and if I don't get to this today, I'm not going to worry about it because it's really something that we're not going to deal with this semester. We're not going to design in this domain, but you could say, look, I notice here that I have a part of my system where it's digital in. Okay, the output of my controller is a set of sequence of numbers. It's digital input, and here the output I'm sampling is it's also digital. Okay, so this is digital. So I could ask myself, can I get a model for all of this? In other words, a model that is of my real world, but it's got an A to D converter on the front end and the sampler on the back end. Can I get a model of that? And so, in other words, how do I get a model of the A to D converter driving my real world, and then I sample it? So this is what I want. This is what I call G of Z. Okay. G of Z is not the same thing as just taking S, G of S, and replacing it by Z. Okay, because I have to account for the imperfections in the system. One is called an A to D converter, and one is called this. Okay? If we don't get to approximation today, I'm not going to sweat it. But this is an issue for some people, because what they would like to do is, if you could do this, if you could convert this and get a C of Z, then what you could do is you could get another model. It's called a discrete time model. And you would draw the diagram like this, very similar to this, except you would put C of Z here, and then G of Z here, and then like this. Okay. That's a discrete time model. We're going to focus our attention 99% of the time of this semester. We're going to use this type of model because it's the classical model. Most people that you're going to come across after graduation, if they know anything about controls, they're most likely going to be introduced to this formal model. Some people say, well, I'm dealing with a digital world. Why not look at a digital model? Well, it turns out doing things digitally requires a whole nother set of math that's different than this one. We don't cover the math for this. We don't cover the math for this in this particular course. Okay? I teach it in another course. But what we will do today is something that is practical, and that is, let's suppose I go through and I design this. I have an expression for this, but now I want to find an approximation so I can write a program to do this. And so approximation 1 is the one that we want to deal with today. Okay? Today's focus. Okay? So the question is, how do I, if I'm given this, how do I get that? And so here's our focus today. Suppose we're given a model C of S. And we sample the world every t units of time. For example, t equal to once per second. Once a second, I'll look at the road. Okay? I have a model, and I decide to sample the world. How do we get a discrete time approximation? In other words, a difference equation, something that I can program. A difference EQUA, a difference equation. There we go. This is our focus. In other words, maybe I have a model, say C of S is equal to 1 over S plus 2. That's just an expression. It's just an expression. Maybe it came out of our design project that we do this semester. It's just an expression in a report or in my mind. It's nothing useful right now until I synthesize it. I have to turn it into a piece of electronics. 50 years ago, you say, what are the R, L's, and C's and the op-amps that I would use to build this expression? Today, what we want to know is, what is the difference equation that approximates that? Okay, so let's recall what does S mean? S is, if I do inverse Laplace transform, this is d by dt of something, remember? In time, if we differentiate, multiplying by s, multiply by s means you're differentiating something. 1 over s means you're integrating something. Okay? So just keep this in mind. Okay, so now let's take a look at the process of differentiation. Okay, let's take a look at an example now. I'm going to draw a graph. This is distance or position. This is time in minutes. No, let's just say hours. All right? So my position is right here. This is on Interstate 85. This is Montgomery. Mile marker 0. The mile marker is 0. Okay, this is mile 0. And 30 minutes later, half an hour, I'm at a different location. Okay. This data point is mile marker 50. This is Auburn. Okay. When I first moved here to Auburn, I think the first mile marker you could get to Auburn was exit 51. Now there's an exit 50. Of course, you could also get off at Wire Road. Okay. So this line describes my position in my car, starting in Montgomery and driving to Auburn. And I get to Auburn in half an hour. This is position. 0 miles, 50 miles. So the units here is miles. All right. What is my speed? Can we get that? How would I get speed from a graph like this? Mathematically, what is it?
Slope.
It's slope. I need the slope, right? let's see, my position is P of t. What is the speed? What is the relationship of speed to position? How do I find the slope of line? I gotta do differentiation, right? Speed is equal to dp dt. But I could also, somebody said rise over run, okay, rise over run. I could also estimate my speed by saying that I only have two pieces of information. I know I started in Montgomery here at 7 a.m. and here I'm in Auburn at 7:30. I only give you two pieces of information. I don't give you this information. I give you this information and this information. These two dots, I give you this information and this information. So I could say speed is approximately, how do we calculate this? Let's call this speed, speed t0, time t0, and let's call this time t1. Let's call this time, this position t1 because t0 because it's associated with time t0, and then t1 gives me position p1. So now I have four numbers: t0, t1, p1, and p0. Can I use these four numbers, these pieces of information? This pair right here is t0, p0. This pair right here is t1, p1. I said that's the only information I give you, this pair, t0, p0, t1, p1. Can I approximate the speed? Somebody said rise over run. How do I describe rise over run using these four pieces of numbers?
P1 minus T0 over P1 minus T0.
Okay, so somebody said rise is P1 minus P0, and the run is T1 minus T0. That's an approximation for finding this. Well, it's exactly for this slope because it's a straight line. Okay. Everybody see how you can get an approximation? Now it's an approximation because maybe I didn't really drive at a constant speed. Maybe what I did is I started off and drove like this, and then I stopped at Tallahassee for breakfast. Okay, roughly mile marker 24, 26. And then I jump in my car later, and then I drive like a banshee like this to get here. Okay, clearly my speed on the road probably far exceeds whatever this is. This is 100 miles an hour, right? 50 miles in 30 minutes, that's 100 miles an hour. But I could have really driven at 120 miles an hour, stopped for a while, and then drove at 150 miles an hour. So it's an approximation because I'm only giving you information here and here. All right? Now, let's take a look at how we can describe this thing. Speed is approximately p at t1 minus p at t0 divided by t1 minus t0. Okay? So what I could say is I could say that this is my sample period, t. Okay? And so I could say this is equal to, if the sample period is t, I'm sampling it now, and then I don't sample again until one sample later. That's why the index goes from 0 to 1. Okay? So I could call this, I could use my notation, I call this p at 0, and this is p at 1 divided by t. Okay? T is my sample period. I only give you information here and here. This is my sample period. Okay? So I can think of this as p of k minus p of k minus 1. Okay? Here k was equal to 1, okay, in my equation. this is starting to now look like a difference equation. It says that velocity, speed, what is my speed? It's approximately present time, previous time divided by the elapsed time. Okay. So if I were to do a z transform based on what I talked about last time, we would call this speed in the z domain. It's approximately equal to, this is now p of z, this is z to the minus 1 p of z. It is delayed, okay? It's one sample back divided by t. So I do a little bit of algebra. This is 1 minus z to the minus 1 divided by t times p of z. So it says that speed is related to position by this filter. Okay. Now remember, in continuous time, speed is equal to d by dt of position. Okay, let's recall this. Speed is d by dt position. But if I Laplace transform this, then I would say speed is equal to s times p of s. Here's speed in the s domain is s times p of s. In calculus, speed is d by dt of position. Now, what I'm saying in discrete time, I'm saying speed is related to position this way. So I stare at all this, and then I come to this conclusion that I'm going to say that the s operator in Laplace is similar to this operator in z. So I'm going to say differentiation is approximately present value minus last value divided by time. Okay. Present sample minus the last sample, previous sample, and this is the sample period. Multiplying position by this expression is equivalent to multiplying position by s. Multiplying by s is equivalent in time as differentiation. Think of this as differentiation. Differentiation in time. Derivative in time is approximately 1 minus z to the minus 1 divided by t. I hope this is a little bit familiar to us. Maybe when you took calculus, when they try to describe to you what it was a derivative, they kind of use this type of idea, right? They say take the present value, minus the previous value, divide by delta t, and then they say in the limit as delta t gets to 0, we get the real derivative. Okay? Okay, so let's go back. Our question is, if I was given this and a sample, how can I approximate my difference equation? Okay, so this is the solution. Okay, this means to get a C of z, I just take C of s and substitute, this means substitute, let s equal to this expression. So as an example, let's suppose C of s was 1 over s plus 2, and t was equal to 0.1. Then C of z is, I write this expression, 1 over s, but wherever I see s, I put in this number, 1 minus z to the minus 1 divided by t, but t is 0.1. Okay. This is my approximation. C of z is just the form of C of s, the filter I designed in the s domain, in the continuous time, and wherever I see s, I put in this approximation. This approximation has a name. It's called the Euler approximation. Okay. Now, any controls engineer worth his salt, or who's been around controls engineering for a while, has another name for this. Okay. It's called the dirty derivative. Why do you think it's called the dirty derivative? It's not the real derivative. It's not really accurate at maybe. It's really accurate when my driving pattern was a constant, because the derivative of this line can be accurately calculated by rise over run. But if I drove like this, it's a lousy approximation for this curve. I saw a hand raised. Yes?
Is the dirty derivative the same as an FFT?
Is the dirty derivative the same as the what?
As an FFT? Fast Fourier transform?
No, it is not the same thing as an FFT. Okay, the question is the dirty derivative the same thing as an FFT? No, it's a totally different animal. Totally different animal. Okay? All right. Let's continue on a little bit. This still is not a difference equation, it's an expression in Z. Let's clean up the algebra a little bit. Oh, so you all help me out. I have to talk and write at the same time, so I might make an algebra mistake, so watch me like a hawk. Okay, so I think the way I'm going to clean this up is I'm going to multiply through by 0.1 maybe, 0.1, and then this becomes 1 minus 0, then minus 1 plus 0.2. Okay, so this becomes 0.1, 1.2 minus z to the minus 1. Let me clean that up. 0.1 divided by 1.2 minus z to the minus 1. Is that okay? Did I do my algebra okay? Okay, let's turn this into a difference equation, something that I can program in C. So I'm saying that C of z now is equal to 0.1 divided by 1.2 minus z to the minus 1. This is an expression in Z. So conceptually, I'm going to write a program. His name is C of Z. Let's give the input a name. Maybe the name is E of Z. And let's give the output a name. Let's call the output U of Z. These are all sequence of numbers. Okay, sequences of numbers, digital. So what we're saying is that U of Z divided by E of Z is equal to 0.1 divided by 1.2 minus z to the minus 1. This is Z expression. The Z expression comes out by approximating C of S. Okay, now let's cross multiply. And I get U of Z, 1 minus z to the minus, U of Z, 1.2 minus z to the minus 1 is equal to 0.1 E of Z. I cross multiply this side and that side. Okay, so this is the same thing as U of Z, 1.2 minus z to the minus 1 U of Z is equal to 0.1 E of Z. Okay? Now this is still expressions in Z. It's not the real world. I want to get back to time. And so what I do is now I do an inverse Z transform. I go back to time. U of Z becomes U of K. Okay? But when I multiply by z to the minus 1, this is k minus 1. U of z becomes U of k in time, but I scale it by 1.2. And over here, E of z becomes E of k, samples. Okay? So what that says is that my output here, I could say, is U of k is equal to 1 over 1.2 U of k minus 1 minus 0.1 divided by 1.2 E of k. My next effort should be this amount of the past effort minus this amount of the error out of my controller. So now this is what we call a difference equation. We're done. This is an approximation for 1 over s plus 2 at t equal to 0.1. At a sampling rate of 0.1, this is the computer program that approximates this funny expression in s. Okay, so this is not a very difficult thing to do. I simply take the design that I'm given, I substitute S with this dirty derivative, the Euler approximation, and I do algebra. Everything else was an algebra step. This is algebra, all this was algebra. This was a little bit of theory. I have to understand that there's a relationship between U of Z and U of K samples, and previous samples are denoted by multiplying by Z to the minus 1. Well, I see my time is rapidly getting away from me. Let me make a comment. Let me close, not close, but kind of do a brief summary. The Euler approximation says that S is approximately 1 minus Z to the minus 1 over T. Okay? I see this approximation used a lot in practice. I have a bunch of mechanical engineers in my graduate class, and every time they want to simulate a problem, they use this dirty derivative, and I groan because it's a dirty derivative. I said, please don't use that. It is so simple. But there are better approximations. Okay, a better approximation goes by several names. One is called bilinear. These are all the same. These are all different names for the same thing. Bilinear, bilinear, bilinear. Okay. It is also called Tustin. Tustin is a guy's name. I'm not capitalizing it because we're going to use that name in a second in MATLAB. And it's also called trapezoidal rule. It's a trapezoidal rule for integration. Okay? You say integration, what is the integration? If I want to integrate a curve, one thing I want to do is I'm basically finding the area under the curve like this, right? And I could do a rectangular approximation for the area under the curve. That's Euler approximation. Or what I could do is I could say, no, a better approximation is this trapezoid. Okay, that's a better approximation than the rectangular rule. So it turns out that mathematically, this is in time, this is P of T, okay, or this is, okay? So it turns out these are all different names for the same math. It kind of depends on how you got to the end. But the approximation looks like this. S is equal to, you still have the 1 over T, you still have the present value minus the last value, but you're going to modify this a little bit by saying, I'm going to take the present value and the last value, this is a 1, these are all 1s, and then I'm going to divide by 2. Present value plus last value divided by 2. What kind of mathematical operation is that? Present exam, last exam, add the two together, divide by 2. What am I getting?
Average.
I'm getting my average exam. So I'm taking the Euler approximation, this is the Euler approximation, and then I'm modifying it by taking a little bit of an average. You may remember, how do I find the average of using what's the area under here? Take this number and this number, take the average, divide by the time, okay? So this is a better approximation. So this is what we're going to do on our computer now. Find C of Z using the bilinear approximation. And we're going to say C of S is equal to 1 over S plus 2. So enter that into MATLAB, and we're going to try to do this before class ends. So figure out a way how to do this in MATLAB. You're going to say C is a transfer function. Its numerator is 1. Its denominator is S plus 2. Okay, so if you're in MATLAB, enter that in. Let's enter in the sample time. T is equal to 0.1. That's the sample period. Okay, so now you got two objects. You should have C, the transfer function, and you should have this. Okay, now to do this by hand, you're going to say C of Z is equal to 1 over S. But what is S? S is 1 minus Z to the minus 1 over 1 plus Z to the minus 1 times 1 over T. 1 over T is 10. Okay? I made the substitution. Exact same thing that I did with the Euler approximation. The only difference is I use a better approximation. Now, is this more difficult than this? Conceptually, no, right? It's just a substitution. Practically, is it more difficult? Yes, because this is a little bit more complicated. So MATLAB says this is a more difficult problem. We're going to give you a tool that will do the work for you. So we want C of Z. This is CZ now. This is C of S. This is CZ. What is CZ? It is a continuous to discrete conversion, C to D. I'm going to convert C using this sample period T, and I'm going to use the Tustin approximation. So type that word in. C of Z is a continuous to discrete conversion. Convert this using this sample period and use the Tustin approximation. Okay. Now, if you want to learn more about C to D, you can do help C to D, and you'll find out that it can do a bunch of other conversions. But this is the practical one. Yes, question?
Shouldn't that be a 20 that multiplier on your approximation? I thought it was 2 over T.
No, I haven't this is 1 over T.
Oh, okay.
I haven't multiplied through by T yet.
Okay.
When I multiply through by T, I would get a 0.2 here. But thank you for checking my algebra. I think I'm correct. All right? So somebody tell me, what did MATLAB tell you C of Z is?
0.04545.
Wait, say so. 0.04545
4545Z
Z
plus 0.4545 over
0.4545 over
Z minus 0.8182.
0 minus 0.8182.
8182. There's an extra 0 in the constant on top.
The second one is 0.04545.
Yeah.
Okay. Now, this is not a very useful form for us because what does multiplying by positive powers of Z mean in time?
That's future.
Future time. Does any of you know future time? If you did, you would know who your wife is going to be, right? You single guys, you would be able to tell the future. You would know what the stock market is doing tomorrow. You would be rich. We don't know future time. This is not useful. We need to do it in past time. We only have history. That's why we have historians, not too many fortune tellers out in the world. We have lots of historians. They don't make money either, but. All right, so how do we get past time? What we do is, we got to take a practical step. We've got to multiply through by Z to the minus 1 and Z to the minus 1. Okay, take our number 0.045, I'm going to just call it 46. I'm going to round off. Z plus 0.46 divided by Z minus 0.8. Okay? This is what MATLAB gives us. It's not very practical because it tells us I need future data. Well, I want to get past data, so I multiply top and by Z to the minus 1. I get 0.045 plus 0.46. And that's 4.5 was actually a better approximation. My round off is not very good today. Okay, now I've got everything in past time. And now I can go through my cross multiply and so on and so forth. Okay? Now we can convert this to a different equation. And I think I'm out of time. I may have even run over. Anybody got the time?
49.
49. Oh. All right, so as I predicted, we did not get to approximation number 2, but it's not a big deal. What we did is we figured out a way to approximate what we're designing in S with a program. Let's stop there. Monday, back in class. Remember, next Wednesday we have exam 1. Make yourself a sheet of notes.